Tonight's lesson is on section 3.1, extrema on an interval. Extreme values. They are the minimum and the maximum of a function on any given interval. They're the extreme values, the extreme minimum low, the extreme maximum high. The values are the y outputs. How low did I go and how high did I go? That's what it means by values. So the relative or local extrema, which is plural for extreme, extrema, these refer to the high and low points of a graph on an interval. So I can have more than just one high and one low on some given interval. It's relative to that situation. Here's an example. Here's a graph. We'll call it function f. And I put down an interval. I did it on the x-axis. So within this interval, I want to find the relative extrema. So this is the relative maximum extrema, the relative minimum extrema, and this is another relative extrema, a maximum. So these are at the turning points. So it's relative to this. So every time I turn around, that high point will be called the maximum. Every time I turn around and it's a minimum, it'll be my relative minimum. Now let's talk about the word absolute or global in calculus. An absolute extrema. It is the absolute highest or lowest values, that's your y output, of a graph on an interval. So let's look back at this one here. The absolute highest on this interval is here. The absolute lowest extrema in this interval is here, within this interval. That is the absolute. But for the word relative, within an interval, every time it turns, it's a high, that's a maximum, and that's a minimum. That's your relative extrema. So yes, we have some new language in calculus. Let's take a look at this picture, another picture. I made this interval a closed interval. So that means here on the graph and here on the graph. So my absolute extrema doesn't just mean my turning points. This is the absolute lowest value, y value. Okay, here's the y-axis in this interval, whatever that is. And the absolute highest extrema or value in this interval happens to be here. So this is the absolute maximum y value. This is the absolute lowest value. Let's look at the extreme value theorem. Abbreviated EVT. This is used on the AP test. You can abbreviate extreme value theorem with EVT. If f is a continuous function on a closed interval, again, continuous means I don't pick up my pencil, on some closed interval, then f is guaranteed to have both a minimum and a maximum value on the interval. This is your y value. This does not mean turning points. Again, if f is continuous on the closed interval from a to b, then f, my function f, is guaranteed to have both a minimum and a maximum y value on the interval. And we'll do an example here in a moment. What you must do is you must check to find these. You must check the critical points and the two endpoints of the interval. So in order to find my guaranteed minimum and maximum, what I'm going to check out are all of my critical points along with the two endpoints. Just as you saw on this last graph, this endpoint was actually the maximum value. But still, before I do an example, I need to define what critical points are, because that's what it tells me to do. I must find the critical points. I must check those and the endpoints, A and B. So what are critical points? It says let f be defined at C. That just means at C, that x value, there's some output value. Here are the critical points. Number one, if the derivative or the slope of f at this value C is 0, so at this C, the slope of this f function right here is 0. The slope of C is 0. That slope is 0. It's a horizontal line. And the other kind of critical points, so where it turns as a critical point from increasing to decreasing. The other one is when f is not differentiable at C. This is a critical point. So we have to go back and we have to look at page 102. I did that off to the side here. On page 102, it gives us two examples where a point on a graph is not differentiable. Where it's a sharp turn, it's not differentiable there. It ends up being undefined. And when it flatlines and you can actually make a vertical tangent, a vertical tangent. Remember, a vertical line in Algebra 1 and Algebra 2, that slope is undefined. Remember, this is a 0 slope. This is a positive slope, this is a negative slope, and a vertical line has an undefined slope. So at this C value and at this C value, it is undefined. That is called a critical point. So a critical point is when it turns from increasing to decreasing, right there. The slope of the tangent line is 0. And the other kind of critical point is where f is not differentiable at that C. Well, it isn't here, and it isn't at this C. Both of these are undefined. Again, here's a larger example. That is where the slope of the tangent line on f at this C value is 0. This is a critical point. C is. And this C is also a critical point. It's a sharp turn. It's a point. And so this derivative would be undefined, or this slope does not exist. So let's try to put this all together. Let's look at this picture. I have a closed interval from A to B, and that will be at this beginning and at this end. I've labeled some points, L, M, N, O, P, Q, R, S, T, U. Again, that's an open hole, so it's not continuous there. So let's take a look and see where my relative extrema are. My relative extrema are. That is my minimum and maximum, any kind of terms. And so it exists at M. Well, that doesn't even exist there, so I cannot call that one. At Q and at T. That's my relative extrema. My absolute extrema, the absolute maximum value and the absolute minimum value in this closed interval from A to B. Well, it looks like the highest is at T, and the absolute lowest, well, I guess I made a mistake here because it should be O, but I can't count that point, so it's really like the point next to it. So let me cheat here for a moment, and I'm going to scoot this over here, and I am going to come down like this. So I'm going to cheat. And so now this new point here, we'll call it L on the closed interval. It's at the very end. That's why it wants me to check endpoints on the extreme value theorem. That is the absolute lowest, or the absolute lowest extrema. This is the highest y value. This is the lowest y value in this interval. So where are my critical points? Let's see. That is where the slope of the tangent line, anywhere on this graph F, it is 0. So that would be here. That would be here. That would be here. So it would be M, Q, and T. But also, the second one underneath a critical point is wherever F is not differentiable. So it is not differentiable right here at P. Can't do anything with point O because it's not filled in. Even though it looks like it's the lowest, the relative minimum extrema, but because it's not filled in, you cannot use that value. You can use the ones right next to it, but I don't need to trick you like that. So relative extrema, that's where it changes from increasing to decreasing, or decreasing to increasing, increasing to decreasing, my relative extrema. My absolute, so within this closed interval, I'm supposed to check all of my critical points. So I'm going to check is M, nope. Is Q, nope. Is T, yep, T is. But I have to also check out my endpoints. And so L. L is my absolute extrema. Next, find any critical numbers. Now I'm just going to give you a function instead of a graph. Critical. Well, I guess what I'm going to try to find and see if there's some value where I'm going to get a slope that is 0. So the first thing I have to do is take that first derivative. I'm going to have to use the product rule. 6x times x plus 2 plus 3x squared times 1. That's 6x squared plus 12x plus 3x squared. Combine like terms, that's 9x squared plus 12x. Now I want to see for what values of x makes the slope of this tangent line 0. In other words, which x values will give me that slope of 0. So I can factor out a 3 and an x. I'm left with x plus 4. Set each of these factors equal to 0. So at 0, I have a critical value. And at -4, I have a critical value. At 0 and -4 on this graph, it goes from increasing to decreasing or decreasing to increasing. Do one more example. I'm going to sketch out a graph. This is -2. This is F. f of x equals x plus 2 to the 2/3 power. That is this function here. So if I don't want to evaluate it at -2, I just want to check out the whole function. I want to see what the critical numbers are. So I'm going to take the first derivative. I'm going to clean that up. But that's a cube root. So I'm going to try to set this equal to 0 to see if I have any increasing to decreasing or decreasing to increasing on this graph. Well, I'm going to cross multiply. So 0 equals 2. That makes no sense. So there are no critical points from a horizontal tangent line, because that's all I was checking for. Is there any place where it does this? Well, now let me check actually at this point here. This should produce an undefined, which happens to be a critical point. So let's see, I've already taken this derivative. Let's put in -2. I should get an undefined. It's supposed to be undifferentiated. You cannot differentiate it at -2. Let's see, that happens to be 0, which that means 0 times 3 is 0. Oh, that's true. It is undefined. At -2, you cannot take the derivative. It is undefined. So -2 is a critical value. Again, we had to check out both criteria. Critical points, 2 scenarios. Number 1, I take the first derivative and see where the slope is 0. At that value, I solve for that x or c value, if you want to call it that, and that's where that slope is 0. But the second kind of critical point, something is happening to my graph, it's where it's not differentiable, like here. It should be undefined. That also is a critical point back on my graph F. Again, your homework is section 3.1, 1 through 18 all. Thank you.